Check, check, test. Anybody hear me out there? We're going to be starting in about 1 minute and 33 seconds. Okie dokie. Hey everybody. I hope everybody. I didn't see a lot of people tuned in when I first checked the metrics a few seconds ago. But I'm going to start anyway because you can back up. If you show up late, you can just rewind, so to speak. And so we'll be not only simultaneously broadcasting, but recording. Yeah. So guys, this is Girl Scouts Love State Parks, and this is something we enjoy doing. Girl Scouts are consistently some of our favorite visitors here at Golden Dale Observatory. Your groups always have wonderful questions and answers. Your leaders are always very good at aggregating your clever questions and organizing them in such a way that we can get to them. And I'm hoping that in the chat during this little talk, I'll see some good questions so that I can respond to them. So on that subject, I want to show you something right now. I'm going to show you live view of the sun, and we got to be quick because it's going to set soon. Check it out. Yeah, so this is the sun right now, coming to you live from our North Observatory Dome, where we're using an advanced telescope with an advanced filter known as a hydrogen alpha etalon, and this allows us to see all these interesting features on the sun. Let me bump it over to the left a little bit here. Wrong direction. There we go. And now I should fit on the screen with it. Yes, I do. Okay, so let's start with this, guys. Currently, you're seeing live HD video, specifically in the hydrogen alpha band. You're looking at the light emitted by ionized hydrogen. And by the way, the sun is made of hydrogen, so you're seeing the sun for what it is. You're seeing it for its composition. But the filter has allowed us to eliminate the glare produced by the sun's heat. The normal reason it's so difficult to observe the sun is not simply just safety, but the fact that all the features that we like to observe are lost in the glare of its incandescence. The sun's surface temperature is 10,000 degrees Fahrenheit. It's energetic enough that it becomes challenging to observe features. If you dim the sun down to make it safe, unfortunately you also dim out the interesting features. So it requires a much more advanced filter than a simple white light filter. White light filters are very common, and many of you have probably looked at the sun using them at some point in your life. They're popular for those Eclipse glasses you've seen, those cardboard glasses. Those type of filters simply use a metallized mylar film that rejects most of the sunlight hitting it. And it does make it safe, but unfortunately you lose the interesting features. This device here, this is called a hydrogen alpha etalon. I mentioned it earlier. This is actually a sort of interferometer, a passive interferometer that allows light to pass through it that we designate. In this case, it's designed to permit the light emitted at 656 nanometers, which corresponds to hydrogen, but it's eliminated all the other wavelengths via what we call destructive interference. So rays of light enter the chamber, and they literally reject themselves via reflection. The rays of light essentially become opposite of themselves and then cancel. That's how that kind of filter works. That's called destructive interference, and it's a technology you've used before in other technologies, other devices, other products. For example, noise-canceling headphones. They do this with sound waves. They essentially re-emit the sound waves inverted, and the sound waves cancel each other out. It's much more challenging with light, and so these are not cheap, and these are not as common as white light filters as a result. Now, the sun is quickly dimming because it's quite smoky here and also cloudy, so I'm going to brighten it up a little bit. The sensor we're using is very powerful, it's very sensitive, and I'm able to overdrive it a bit, and we're able to compensate for the smoke, at least for now. So before the sun starts to disappear, I'd like to get right down to it and start identifying features for you. So let's zoom in here. Let's go over here. Let's find something that you've probably heard of before. You see these dots here? These are called sunspots, and those are regions on the sun's surface that are cooler. They're not cold, but they are cooler. Less hot is a better term, probably about 5,000 or 6,000 degrees. Those are areas where convection, which normally carries heat to the surface of the sun, has been disrupted by electromagnetic fields. And so those areas are able to cool, and that's why they look darker. But you might notice right next to it a dark line that almost looks like a smiley face. That's called a filament, and that's a very different type of feature. Sunspots are easy to see. You can observe them with those white light filters I mentioned earlier. But things like filaments require this more advanced technology. We'll talk more about what those are in a second. Just give me 1 second here. I'm going to adjust it again. Let's go over here to the edge of the sun, and you see a very famous type of feature here. Many, many, many people, when they see something like this, they assume it's what's known as a solar flare. This is not a solar flare. Flares are explosions on the sun. This structure here is known as a prominence. Prominences are not fire or flame, and by the way, the sun is not burning. It is not a fire. Prominences are areas above the surface, gigantic fields of hydrogen plasma, hydrogen and helium, held aloft by a very powerful magnetic field. You might notice there's a curving shape to it. It looks like an arch. That's because that's how magnetic fields tend to propagate, in loops and arches. So you're seeing hydrogen plasma held above the moon. It's funny. Held above the sun. And just so you know, this is not a small structure. The Earth would fit in that gap right there beneath this prominence. So these are not small structures by any means. Yeah. We'll talk more about why the sun has a magnetic field in a minute and what it looks like. But I just want to make it clear that's what this is called. This is a prominence. Now the filament, that dark smiley face thing, and this one here, and this one here, and this one here, there's filaments all over the sun today. Those actually should not have a different name because filaments are simply prominences that are facing towards you. So since they're coming towards the Earth, they look like dark lines as opposed to arches. I'm going to check the chat really quick, see if there's any questions about all this. Let's see here. I don't see any at the moment. That's fine. So, moving on. We move over here to other parts of the sun. These bright areas you see, and then one up here too, these are called plages. These are regions on the sun's surface that are hotter. As a result, they look brighter. And it's funny, many people are confused by that because you'll notice that they're next to sunspots, and as you just heard, or perhaps already knew, sunspots are cooler. These are cooler areas on the sun. So the reason there's a temperature difference is because we have the opposite thing happening. Magnetic fields are dredging material down, which disrupts convection. You get these cooler spots. But then magnetic fields can also dredge material up at a rate of speed faster than convection, and you'll get these hotter spots. Additionally, the plages are hotter because of the literally trillions of amps of electrical current flowing through the material. You guys are probably aware of the fact that magnetic fields, when moved over conductive materials, can actually cause electrical charges to build up and for current to flow as a result. So these regions are so energetic electrically because of the powerful magnetic fields that are responsible for them. Again, I'm going to talk more about that in a minute, but I just wanted to get that out of the way. We want to make sure we see these things before the sun starts to become unobservable. As you can see, it is getting darker quickly. Let me see if I can adjust our sensor a bit more. We're starting to get to the maximum level we can adjust it. Give me 1 second. Let's get a little bit brighter here. It's a little better. Hold that thought. You know what? I'm going to change this setting a little bit here. And now we're starting to really overdrive the sensor, and you can start to see some of the pixels that are kind of malfunctioning, those little bright dots. Those are not stars. Those are pixels that are malfunctioning. And you don't tend to notice that until you start to really exceed the settings on the sensor. It's really quite impressive, though, that we can do this. If you were to look at the sun right now, it would not be bright. We're looking through a lot of smoke and clouds right now, and yet you can still observe these features because you live in the future where we have these wonderful camera technologies at our disposal. We're also using a telescope with a fairly fast f ratio, which means it's using a lot of the light. It's not wasting it on magnification. That's why we're able to see the entire sun, by the way. The combination of that, a very large filter, and a very sensitive sensor allows us to see the sun so well, even when it's actively setting into the clouds. Now, I'm going to continue on in a second. I'm going to check the chat again. By the way, I don't see any chat. If you guys have anything to say, feel free to add it. We love questions. In fact, we want you to ask questions. The whole purpose of this is getting to learn things about the universe. Golden Dale Observatory in your living room, so to speak. I think that's how it was advertised. Yeah. So, I'm going to keep on going. While the sun is still observable, I'm going to really magnify it now. Excuse me. I'm really not magnifying. I'm going to really overdrive the sensor. I'm overexposing it on purpose. And notice that when I do this, we can very clearly see lots of prominences that we didn't notice earlier. See this? These prominences were not as bright, but they do come out when I overexpose the sensor. There's one there. It's kind of interesting. Looks like a loop. We'll get to that. We'll talk about why that is. So today we have lots of prominences around the sun. The really nice one is over here. It's very impressive. Yeah. Okay, I'm going to change the settings again. Let's see here. That's actually quite a nice image given the conditions. You'd be surprised if you saw the conditions right now. You'd be surprised that we can achieve this. So let's talk about the sun. I wasn't planning on doing a solar show, but with the conditions as they are right now, the sun is the only thing we can look at, and that's going to change very soon. So let's talk about the sun while we can. I already mentioned that the features you see on the surface of the sun are caused by electromagnetism. This is often surprising to people. Many people know, correctly, that the sun is powered by nuclear fusion, and they assume there's some connection to the surface in that regard. It's true that the sun is powered by fusion, and that is the source of the sun's heat. But fusion, which is a nuclear reaction, not a chemical reaction, occurs deep inside the sun in the core. The core of the sun is, of course, not what you're observing right now. The surface of the sun is very indirectly heated by the extremely intense activity in the center. Because the sun is so enormous, because we're distributing this energy over such a vast surface area, there's a gigantic temperature difference. The core temperature of the sun is 27 million degrees Fahrenheit. The surface of the sun is about 10,000, like I mentioned earlier. So, fusion is not occurring on the surface of the sun because it cannot. Fusion is a reaction that does not want to occur because atoms naturally repel each other. They won't go together. So, simply put, it takes a lot of energy to fuse atoms, and there's not enough energy, not nearly enough energy at the surface to do that. The surface features, although very entertaining and interesting scientifically, are kind of like window dressing. They don't really have much bearing on the fusion that defines the sun, that powers the sun. And like I said earlier, they're all caused by magnetic fields. We're going to talk about why the sun is so magnetic in a second. It is indirectly linked to fusion because the great energy of the sun, the great heat of the sun, makes it possible. Some of you have heard the sun is a giant ball of burning gas. That's actually wrong twice because the sun is not a ball of gas. It's too hot to be a gas. It's in a state of plasma, not gas. And it's not on fire. It's not burning. Fire or burning are chemical reactions, whereas fusion is a nuclear reaction. As you can see, the sun is rapidly dimming now. Let's see if we can fix it. We're really pushing the limits of our technology. It's still there. I can still see all the things. That's impressive. You are actually, I think, the first group to observe a live stream of our sun using the new technology we've recently installed in our North Dome. We have 2 domes here at Golden Dale Observatory, and this particular setup is quite good. It's very unusual that you get to see all these kind of features in the same exposure. Usually they're mutually exclusive. For example, it's typical that if you're able to observe surface features, the edges are not going to be exposed properly. It's going to be too dim. But we've developed this technique which allows us to do both at the same time. So you're really seeing right now all the interesting kinds of features that one could expect to see on the sun if you have a nice solar telescope. I wonder if there are any questions about that. I'm sorry, how hot is the core of the sun? Someone just asked. So the core of the sun is 27 million degrees Fahrenheit. We can measure that directly, believe it or not, because the sun's core emits neutrinos. Neutrinos are ultra-low mass particles that move at the speed of light, and they are emitted in huge quantities by nuclear reactions. And so because they are able to move through regular matter, we can actually see into the sun's core using, logically enough, neutrino observatories. Now, the surface of the sun does not emit very many neutrinos because nuclear reactions are not taking place there. Ironically, we know more about the sun's core than we do about the layers of the sun between the core and the surface, because those layers also do not emit neutrinos. I think that's pretty interesting. By the way, 27 million degrees is the core temperature of the sun, but that's not the minimum temperature a star needs to be to undergo fusion. In fact, the core of the sun is hotter than it needs to be to maintain this process. The core of a star needs to be around 22 million degrees Fahrenheit in order for this reaction to take place. By the way, there are stars that are smaller than the sun that are going to be even closer, very close to that temperature, that critical thermal point where they can actually engage fusion. If an object is unable to achieve those temperatures and sustain them, if fusion cannot be sustained, then that object cannot be considered a star. You might be aware of the fact that not all stars succeed during their formations. In fact, there's an entire class of failed stars known as brown dwarfs. We'll talk about those in a minute. Oh, we're really losing it now. Look at that. It's starting to get real dark. Let's see. I'm going to keep trying, though. It's okay. If we lose the sun, which we will soon, it's fine, because we will essentially show you some footage of it. Oh, wow, I'm starting to get maxed out now. Oh, there we go. Oh, now I want you to notice something. You might notice the frame rate is dropping, and that's because we are now having to do fairly long exposures to achieve this image. So essentially a significant fraction of a second in this case is required for us to be able to maintain our view of the sun because we're looking through so much smoke. Are there any questions about that? Those of you who are just tuning in, I want to make it clear that those little dots on the screen are not stars. I know they look like stars and people get excited about that, but those are simply hot pixels on our sensor. The reason they're showing up is because we're driving the sensor so hard to compensate for the low luminosity caused by the clouds and the smoke. We're looking through quite a lot of wildfire smoke, unfortunately, right now. Yeah. So, before I continue, let me check this chat again. Okay, I don't see any other questions, so I'm going to continue now. I'd like to discuss why the sun's magnetic. I already briefly mentioned it has something to do with the fact that it's hot. The reality is that the sun is so hot, and I mentioned earlier, that it's not in a state of gas, but plasma. Now, plasma is the fourth state of matter. Plasma is, by definition, highly energetic. Atoms that are ionized and remain that way for an extended period of time are considered in a plasma state. And some of you might be learning this in school right now. Ionization is the charging of an atom when it has the wrong number of electrons. So let me take my head off the screen really quick here, and I'm going to show you a chart that you might find interesting. So here is an image. Hold that thought. Here's an image depicting the phases of matter. So as you can see, there are four classical ones that we talk about most often. There are some more exotic examples of phases of matter, but these are the ones that you should be learning about in school. And really, the only thing that separates them is energy level. So if you freeze something, you've lowered its energy enough that the atoms become so locked by their own electromagnetic attraction that the substance resembles the behavior of a solid. If you energize it a little bit more, the atoms can move freely enough to behave like a liquid. And of course, if you energize it more, it can behave so freely that they fill voids and become what's known as a gas. And if you add even more energy, you can transition from gas to plasma. And as I mentioned earlier, the primary difference between these two states of matter is charge. Notice these little negatives, those are electrons. In a plasma state, the atoms will not have the right number of electrons. They're either going to have too many or too few. This causes them to achieve a charge imbalance, and they want to become balanced. As a result, atoms in an ionized state will try to seek out other atoms, forming molecules and returning to their ground state, their charge. Also, they're going to very readily convey electrons, atom to atom to atom, and so as a result, plasmas are very conductive. Are there any questions about that? I'm going to tell you more about that in a second. Let me put my head back on the screen here. Now, I have a toy here on my desk, this ball. This ball contains oxygen at a pressure very similar to the pressure you might find in the upper atmosphere at an altitude of about 80 miles. It also contains a Tesla coil, which I'm going to turn on right now. Watch this. You see the green there. See it going to my hand? This is no longer gaseous oxygen. It is now ionized. It's now in a plasma state. Do you see that? You might be amazed to learn the plasma in this globe is more conductive than solid silver. Now, silver is considered a very good conductor, isn't it? Let me show you it a little bit bigger. So, the very good conductor in this case is oxygen. Now, it's funny because oxygen is not normally considered a conductor. It's considered an insulator. But because we've ionized the gas into a plasma state, now it's very happy to convey electrons, and this makes it very conductive. This is very, very, very important when it comes to discussing the way the sun behaves, because the sun, as I mentioned earlier, is not in a gaseous state. It's too energetic to be a gas. It's in a state of plasma. That means the sun is very conductive electrically, and that happens to be one of the very main reasons that it is so energetic electromagnetically. Now, I'm noticing we're really losing the sun now. So we're going to say goodbye to our live sun view. I'm glad you got to see it. We got about 20 minutes. That was good. I was concerned we weren't going to get to see it, so that's nice. So now, let me show you something that might shock you. I'm going to show you a map of the sun's magnetic field, and this may be a little strange looking to you. Check it out. Look at that. First thing you notice is the sun has more than one north and more than one south pole. In fact, it has millions of dipoles, which are north and south, and they're always changing. This map illustrates the different poles by color coding them. So you'll see different lines of electromagnetic flux, in this case denoted by the different colors. Now, this map was generated in August of 2017, and that is a date some of you might be familiar with. There was a famous solar eclipse. In fact, this was generated the day of the eclipse. And I want to show you that not all things are random or chaotic. I want to show you a picture that someone took of the eclipse. And what you immediately notice, of course, is that the corona, which is the sun's atmosphere, if you wish to call it that, clearly adheres to the contours of the magnetic field. So the sun's magnetic field is very important when it comes to understanding why its surface behavior is what it is. Notice there we have the magnetic field, and here we see the corona adheres to it. But notice these loops and arches that are not on the limb. Those are responsible for those things we talked about earlier, like filaments and prominences. Yep. If the magnetic fields are converging on an area on the surface powerfully enough, it can disrupt convection, like we talked about, and you'll get things like sunspots, for example, or the plages that we talked about. Let's see if there are any questions about that. Nope, not yet. So now, let's look at the same thing, but we're going to do it in 3 dimensions. Behold. Look at that. Oops, wrong. I'm going to put this over here. There you go. So this is a video that is not depicting the rotation of the sun. What we're doing here is we're rotating the model that we've created of its magnetic field. The reason I point that out, the sun does rotate, but it takes 25 days to do so. So in that time, these magnetic fields would have changed substantially. It's important to keep that in mind. The sun's magnetic field is constantly changing. In fact, the map I'm showing you now, and also the 2-dimensional version I showed you, that would have been obsolete only a few minutes or hours after it was generated. And that's because the magnetic field of the sun is so complex and convoluted, it's so chaotic. Yeah. I wonder if there's any questions about that. I want to repeat, guys, feel free to chat, feel free to ask questions, feel free to say things, and we will we'll answer those questions happily. Yes. So that 3D view of the sun's magnetic field, although it's very interesting and informative, is definitely not indicative of the state of the sun today. Its magnetic field is constantly changing. Now, I'm going to show you a seemingly random picture, but I promise it's not. Here is some lightning over one of our domes here at the observatory. Now, this lightning is plasma air. So the air itself has been ionized into a plasma by high voltage. Very often, if you ask someone what lightning is, they'll say electricity. No, it's not. A lightning bolt is actually just plasma air, but it is being ionized by high voltage, in this case high voltage static electricity. By the way, just for the fun of it, I'll tell you that's a picture of our old North Dome. Notice it's silver. Our building looks a lot different now. You may have heard we had a big upgrade recently. So this is an old picture. Now here's a picture taken at the Maryhill Stonehenge. This is a war memorial that's very close to us, and got some lightning over that. It was a few years ago. We don't get a lot of thunderstorms here in Goldendale, Washington, or really in most of the state of Washington, so I always try to take pictures of them whenever I can. And again, what you're seeing here is air ionized into a state of plasma by high voltage. The air itself has gone from being a good insulator to an excellent conductor, because all the atoms that are in that bolt are very angry because they have the wrong number of electrons and they're trying to fix it. This is why lightning is so powerful, because it's a highly conductive event. You have essentially a wire run across the sky where electrons are able to move freely. This is why a lightning bolt will conduct tens of thousands of amps in only a few milliseconds. The bolt itself will be hundreds of millions of volts, but it's not the voltage that's impressive, it's the current, the amperage that's so shocking. Shocking, that's funny. Yeah. Now, I just mentioned tens of thousands of amps, but you might recall when I was talking about the sun, I mentioned trillions of amps. Trillions upon trillions of amps of electrical current are flowing through the sun. And whenever electricity flows through anything, you will see an electromagnetic field being generated. That is the source of the sun's magnetic field. By the way, this is not unique to stars, and by the way, the sun is a star. This is also how gas giant planets get their magnetic fields. So they actually do contain plasma, hydrogen, and helium, just like the sun does. Because it's in a state of plasma, it's very conductive. Enormous amperages flow through it, and we get enormously powerful magnetic fields. It may not surprise you to learn that Jupiter has the strongest magnetic field of any planet in our solar system, but it's relatively small compared to the sun's magnetic field. The sun is definitely the most powerful electromagnet in our solar system. And it's interesting when you consider the fact that it's made of hydrogen and helium, and neither of those materials are considered conductive. This is why it's important to remember the phase of matter. If it was gaseous hydrogen and helium, it wouldn't do very much interesting stuff in this regard, but because it is ionized, it's able to react electromagnetically. And that's why the material that we see on the sun is attracted to the magnetic fields. That's why it moves in response to their motion. Now, since we've lost the sun to the clouds and the smoke, let's show you some video that we shot of it here at the observatory. Let's see, let's find a good one. So this was a few days ago. Now, this is some pretty impressive behavior here. So I want you to look at that, of course, lower right section there. Very active prominence. This is about 3 hours and 15 minutes of activity, and we sped it up about 1,100 times. So this is about 1,100x speed. This time lapse allows you to see the very interesting behavior of the plasma hydrogen. You can see how it flows almost like water, and that's responding that way because it is charged. The thing about plasma is it can both simultaneously attract and repel itself, and so that will lead to very unusual and chaotic motion. It's one of the reasons why the sun's magnetic field is so strange and so random, because the magnetic fields are responding to each other, and they're also being being generated by material that is itself moving in complicated ways. Plasma tends to be rather chaotic by its nature. It will move strangely. So you have magnetic fields affecting each other. You have plasma itself affecting other plasma because charges are different. And then there's other things too. The sun mixes and stirs and twists itself. The material of the sun is not solid, of course. It behaves kind of like a liquid. It actually has a very long name, an electromagnetohydrodynamic fluid. And this material acts like a fluid partly because it is charged, and it moves in complicated ways. The sun does not rotate uniformly. If it did, then it would be much less interesting to watch. The sun's chaotic motion is one of the reasons why its magnetic field is so interesting and so constantly changing. Some of you might be aware of the fact the sun has an activity cycle. Every 11 years, the sun's magnetic field flips. But it doesn't actually flip. It goes crazy. When it's done going crazy, it's upside down every 11 years. Yeah. Any questions about that? I don't see any. Okay. We shall continue on. So yeah, if you want to see activity like this on the sun, it matters when you try. So because of the 11-year activity cycle, sometimes you'll look at the sun and see all kinds of cool stuff happening, and sometimes you'll look and it will seem almost blank. And this is frustrating for us at the observatory when it looks blank, because people come here to observe the sun. There are some days where you won't see all this interesting activity taking place. So I'll show you a chart that might interest you. This is the 11-year sunspot cycle I mentioned earlier. And you can see that it clearly goes up and down. Sunspots are not really what's cycling, though. I don't prefer to call it the sunspot cycle, because sunspots are simply a symptom, if you will. They occur because of the strong magnetic field disturbance. And as you can clearly see, it does change. Over the last few decades, the sun's been getting quieter. And I will tell you, the most recent solar minima, which is right around here, was incredibly quiet. In fact, we saw almost nothing for months at a time. Many months with no sunspots or any other interesting activity to observe. So it's kind of frustrating. But it was also interesting to see that. We're now moving up into the next solar max, which will be around 2025, give or take a year or two. I should also mention that this cycle is not exactly 11 years. Yeah. So the solar activity cycle is all essentially affected by the magnetic field of the sun and how convoluted, how disturbed it is. Now here's this video again without my face in front of it, and you'll see an active region where my head was, right over here. And then you can see it's very active. Things are changing in there quickly. Now, let's show a little footage from NASA for a second. Here's a nice video from NASA comparing solar minima to solar max. And as you can clearly see, solar minima has a lot less stuff going on versus solar max. Now let's keep watching this for a second, because it's going to compare things. There's sunspots. See, there's none on the left, and there's a whole bunch on the right. See that? And now we're going to compare the magnetic field. Watch this. Notice the magnetic field on the left. I'm going to pause this for a second. Notice the magnetic field on the left is symmetrical. It looks almost orderly. It almost looks predictable. See that? But then notice it on the right. It looks extremely chaotic, convoluted. And it's always changing too. Yeah. So big differences between the magnetic fields during solar minima and solar maximum. Now keep watching here, because I'm going to show you something else. The sun's corona you could refer to as the atmosphere. And I'm going to pause this again. Please note, there's a difference here in the corona. Not only do we see more activity going on during solar max, but we see this big hole here. Sometimes you'll have coronal holes during minima too, but they're less common. Coronal holes are interesting. You could think of it almost like a hole in the sun's atmosphere. And when coronal holes occur, it allows solar wind to stream out at a higher velocity than usual. Now, solar wind is not really wind. There is no wind in space. Solar wind is the term we use for the constant barrage of particles that leave the sun under radiation pressure. It's mostly hydrogen and helium ions. Solar wind affects the solar system. It can hit planets and cause changes to their atmospheres. Solar wind is actually a very destructive force. It's the reason that Mercury has lost all of its atmosphere. By the way, here's a picture of the planet Mercury. This is not the moon. Every time anyone ever sees this, they always say, oh, that's the moon. Mercury has lost its atmosphere to solar wind ablation. So anyway, something positive can also come of this. When planets are struck by these particles, it can ionize their upper atmospheres if they have one. And a few weeks ago, we did indeed have a wonderful geomagnetic storm that led to some very pretty aurora. So that was a neat thing to see. We'll talk about that more in a second. But yeah, the aurora of Earth are caused, a lot of people don't know this, by solar wind, specifically solar ions ionizing the upper atmosphere. So here's a video of some aurora that we just had here. Check it out. I'm going to put my head back on the screen in a second, but first I want you to watch that. All those things you see moving around, those are all satellites. That's the satellite right there. So this was quite a nice surprise. This was last week, and it was quite a few hours actually. Earth's magnetic field was heavily disrupted, and it was by a solar wind stream emitted by a coronal hole. The video is going to restart, and when it does, I'm going to put my head back on the screen. There you go. So you can see here the aurora moving, and you might notice it moves in a way different from the rotation of the Earth. You can see the Earth's rotation in the stars. See the stars moving? But the magnetic field of Earth is moving much more rapidly and more chaotically during these events than simply the Earth's rotation would cause it to. And so and you can literally see the contours of Earth's magnetic field when you look at those pillars, those vertical pillars, you're literally seeing the edges of these gigantic lines of electromagnetic flux that I showed you in those videos and pictures. See that? Now, the aurora's color is directly related to what the air is. Just like lightning, this is ionized air. Air is mostly nitrogen. Nitrogen produces a pinkish purple glow when it's ionized. That's why lightning is pink. Did you notice that in the pictures? The aurora tends to be pink for the same reason. The green that you saw, especially in the beginning of the video, that's caused by oxygen emission. Any questions about that? Let's go back to our chat really quick. How do you know the sun flips after every 11 years? So the sun itself does not flip. It doesn't physically flip. The magnetic field changes polarity, and we can measure that directly and indirectly. Light from the sun has to pass through the magnetic fields, and this will cause the light to be slightly polarized. Those of you who don't know what that means, light rays don't have to all move in completely random, chaotic ways. They can sometimes move horizontally or vertically. We can measure the polarization of light, and we can tell the magnetic polarity that it passed through, essentially, via this process. That's one of the ways we do it. We also do it just by literally watching the behavior, just watching the movement of particles on the sun's surface. Those prominences are flowing directionally, and the direction actually you can actually infer from the direction the charge. So what ends up happening is the sun's magnetic field is always changing, and we can tell overall what its polarity is hemispherically. So let's see, I'll say the top is north and the bottom is south. Every 11 years, that relationship flips. But like I said, it doesn't really flip. It goes crazy, and then when it's done going crazy, it's upside down, so to speak. But I want to repeat, the sun itself is not flipping. It is the magnetic field polarity that is changing. I have a video for that if you're interested. So here is a video of the magnetic field changing over the course of years. Get my head out of the way for a second here. So as you can see, the blue and the red indicate polarity, and you can see that every 11 years, roughly, it's not exactly 11 years, we see this change. So those white dots you see being drawn on the chart on the lower right are actually the positions of sunspots. Notice the sunspots seem to coincide with the strongest magnetic field disturbances. That is not a coincidence. Like I said, sunspots are not doing anything, so to speak. They are a symptom. When the sun's magnetic field is more crazy and convoluted, we see more sunspots. Any questions about that? I'll go back to this video just because it's fun. I was pretty happy with this. We don't get to see the aurora like this very often here. So, by the way, on that subject, Goldendale Observatory is not that far north. We're down on the border with Oregon in Washington, and people will unfortunately drive down here to see the northern lights when they hear there might be a chance to see them, and that is the wrong decision. They should go up. You should go as far north as you can. This is, of course, assuming you're in the northern hemisphere. If you're in the southern hemisphere, you should go as far south as you can, because there are also southern lights. The southern lights, or the aurora australis, not as famous as the aurora borealis or northern lights, because there are less people down there to observe them. Yes, there's plenty of humans in the northern hemisphere who are in the right latitude to see the northern lights. Yep. Looking for questions. Let's hear some questions. Don't see any right now. Okay. So, before I continue, like I said, I wasn't planning on doing a solar show, but I'm kind of doing that right now because the sun was the only thing we got to look at today. But I will have an opportunity near the end, which is coming up, to talk about other topics if you're interested. So feel free to post them, and I will discuss them. By the way, the color of things, like I mentioned the pink nitrogen and the green oxygen, that is not, of course, limited to Earth, is it? Astronomers love the science of spectroscopy. You can tell what things are made out of without actually being there, and that's very important. Because in astronomy, we don't have the luxury of collecting samples. You can't go and get things and bring them back to your lab for study. So studying the color of light tells us all kinds of things. It tells us if something is in an atomic state, or if it's in a molecular state, if it's ionized, if it's not. It tells us what isotope of the element it might be. That's the neutron configuration. Different elements can have different isotopes based on their neutron counts. We can tell that with color of light. You can tell if something is speeding towards you or away from you. Towards you, you'll have the light being blue shifted. Away from you, the light is red shifted. And we can measure that very precisely. And it allows us to detect very, very subtle motion of space bodies. Again, because we studied the color of light. We might talk about that more in a second as we start to wrap it up. I will show you a colorful space object here. This is what's known as a planetary nebula. These are not related to planets in any way. They are one of the worst named space objects. Planetary nebulas are not stars that have exploded, although they unfortunately will often be described as such in like YouTube videos and on magazines and stuff. This is material that was ejected from the surface of a dying low mass or intermediate mass star. By the way, our sun will produce one of these when it dies. Our sun is considered an intermediate mass star. The colors are not random. In fact, the orangey color there is a mixture of helium and some hydrogen. But that aquamarine color, that bluish green, that is actually oxygen emission. Yeah. It's right there. You can tell what something's made out of based on the color of light. Here's a different example of the same object. By the way, both of these pictures are of M57 the Ring Nebula, which is a famous planetary nebula. One that you can look at through our telescopes here if you visit in the summertime. This is a famous summertime space object. But I wouldn't recommend doing it tonight. We have a big full moon out, and we're almost full. It was full 2 days ago. And it's also quite smoky and cloudy. So those are not the conditions for observing nebulas or galaxies. You might notice there's a galaxy in that picture right there. So these are the kind of things you need darkness to observe. This is the Helix Nebula. This is a different one. Same kind of object, though. And again, you can see the consistent colors there. Here's some more. Notice they're not always round. That's worth mentioning because the name of planetary nebulas is based on their roundness. William Herschel famously saw them and thought, oh, these must be planet-related, or at least planets are round, so I'm going to name these after planets because these are also round. It's not a very good reason to name them that because, like I just showed you, they're not all round. Look at the Bug Nebula there. Clearly not round. Yeah. Questions about that? Now, let's look at another colorful object. You may have heard of this. This is really famous. This is the Crab Nebula. This is a famous supernova remnant, so the results of the death of a star that did blow up. So this is actually a star that exploded. And again, all those colors indicate what we find in there. Now, this is quite profound because when we study the spectra of the supernova remnant, we actually discover all of the elements, all the naturally occurring elements can be found in the spectra of this object. And there's 2 reasons for that. This was the result of the death of a star that was recent. So it was a star that died in the modern universe. And a lot of people don't know this, but the modern universe is more chemically enriched than the ancient universe. As the ancient universe grew older, we had a larger and larger quantity of heavy elements accumulate because there are various mechanisms in the universe that create heavier elements from lighter ones, including supernova remnants. So not only does this supernova remnant contain material that was inherited from previous stellar generations, it also contains material that were created in the explosion. There are certain elements that can only be synthesized in incredibly violent events like supernova explosions, specifically in this case a type 2 supernova explosion. So the colors of this are resultant not just from its inheritance from previous generations of stars, but also the material that was produced during the explosion. Yes. And again, the color is very important to us because we can see what it is without actually being there. This particular supernova remnant, the Crab Nebula, occurred in human history, and humans saw it. So in the year 1054, a star became so bright in Taurus that you could see it in broad daylight. And for years, it shone so brightly that you could even read by it. It would cast shadows. And we later figured out that that bright light they saw was a star blowing up. And so this particular object is 7,000 light years away. So essentially, this explosion only happened 8,000 years ago, give or take a few decades. And so because of that, we have an already metal, and by the way, the word metal refers to chemical enrichment. So we have a metal-enriched object that blew up and seeded the universe with new elements. Not new to science, but larger quantities of elements that are traditionally very rare. For example, a very rare element would be uranium, and there's uranium in that expanding cloud, and we can determine that with the color of light it emits. Any questions about that? Type 1 and Type 2 supernova, I think, is your question. So someone's asking, what is the difference between a Type 1 and Type 2 nebula? No, those are supernova types. So a Type 1 supernova occurs when a white dwarf star detonates after accreting too much mass to prevent runaway nuclear fusion. Now, I'm going to go back to that picture of the Ring Nebula, and I can zoom in here, and you see a bright object that you think is a star, but that's actually the collapsed core of that star, and it's a white dwarf. White dwarfs are the collapsed cores of low or intermediate mass stars. They are not undergoing fusion. White dwarfs are white because they're hot, and the reason they're hot is because they have a lot of residual heat from the life of that star, compacted into an extremely tiny volume. White dwarfs can be about the size of Earth. That's amazing when you consider that a star like this would have been about 1,000,000 times larger than the Earth. So imagine the core of that star collapsing down to something as small as our planet. That's why their temperatures are so high, because you've taken the energy and condensed it into a small surface area. Anyway, not hot enough to undergo fusion, but if a white dwarf is orbited by another body, or it orbits another body, and it's able to steal mass from it via gravity, eventually the mass will become high enough on the white dwarf for it to collapse and experience runaway fusion that causes it to annihilate itself. That's what's known as a type 1 supernova. Type 2 supernovas are a more natural event. This is what happens at the end of the life cycle of a high-mass star. High-mass stars are so enormously heavy that when they collapse in on themselves at the end of their lives, they collapse so quickly that they create shock waves so intense that it will, again, touch off runaway fusion and blow the star up. Again, this is the natural end of a high-mass star's life, the type 2 supernova. Unlike a type 1, which is essentially a freak occurrence that happens in the case of some white dwarfs that are lucky or unlucky enough to be orbiting something or vice versa and being able to steal mass from it. In both cases, however, you're talking about a star blowing up. In the case of a white dwarf, it's a detonation of a dead, collapsed remnant. In the case of the type 2 supernova, we're talking about the star itself exploding, the layers of the star above the core and the core itself. That being said, usually, in the case of high-mass stars, the core will collapse into one of two extreme types of objects, and many of you probably know what I'm going to say, either neutron stars or black holes. Only the most massive and rare of stars will produce black holes when they collapse, but they will blow up in the same way a regular supermassive star will that will create a neutron star. And by the way, there is a neutron star at the heart of the Crab Nebula. You don't see it in this picture, but within the center, there is a rapidly rotating ball of neutrons, very small, less than 20 miles across. And that is a essentially collapsed core. It used to be made of regular matter, but it's so collapsed, so crushed by its own gravity, that it's no longer containing protons. Protons and electrons have been crushed together to form new neutrons, and the neutrons that were already there are pushed up against other neutrons. So the neutrons are holding up the object from further collapse via their own strength, if you will. That neutron star is the collapsed core of that dead supergiant star. Any questions about that? I don't see any. Okay. Now we're going to be done here in about 14 minutes. I'm hoping to hear a few requests or something before I move on. 1 second. Checking my gadget here. Okay. So, when it comes to the colors of light in the universe, you will often see pretty pictures like this. Many of them are visible light images, but we are not limited to visible light. We have invented telescopes that can see other wavelengths of light. Most famously, the one that's been in the news a lot lately, the James Webb Space Telescope, is an infrared space telescope. And you can see light, in that case, below or beneath visible light. But there are also telescopes that can see above it as well. For example, ultraviolet, or X-ray, or gamma ray. In the case of things below infrared light, you have microwaves, or radio. And we have invented the means of observing the universe within every one of those sections of electromagnetism now. And we can learn things in all different ways. Not everything in the universe is hot enough to emit visible light, for example. Some objects are only warm enough to emit infrared, or maybe cool enough to just barely emit radio waves. So yes, we're not limited to visual spectra, and all the pretty colors you see, in this case real-life colors, are not always that useful. Sometimes we want to see colors that you cannot see. And if you were to try to observe these things, we can collect the data and do the math, but if you want to see the actual picture, we need to colorize it. So I'll show you some infrared images before I wrap it up. That would include images that used to be infrared that we converted to visible so that you could admire them. Yeah. Questions about any of this? Let's see. Thank you very much. Okay. Now, I think it might be worth ending the show. We're not going to talk about the sun anymore. but I do want to talk a little bit about those colors we talked about, specifically the elements. I'm going to show you some grade school science here really quick. Here is a chart that illustrates the fact that different elements have different colors. Now, as you can see, some of them are quite obvious. Neon is associated with an intense orangey red color, whereas sodium is very obviously yellow. So there's the yellow of sodium, the orange of neon. And then you have some more that are more mixed. We don't create charts like this to help you see what something is with your eyes, but it is a tool used for figuring out what elements we're dealing with. Yeah. On that subject, let me put my face back on the screen here. I'm going to take this stick and I'm going to see if I can ionize it into a plasma. If I can't, I'll use something else. This is an experiment for all of you. Let's see if this works. Oh, just barely. So you might see some orange there. See the orange? So the green of oxygen, but now we have the orange of neon. Yeah. So different elements, different colors, right? Now, I just showed you a chart that illustrated the fact that different elements emit different colors. Now I will show you a chart that illustrates that different elements will also absorb different colors. Now, this is essentially the opposite of what I just showed you. These rainbows you see are the light emitted by a bunch of stars. These are the stars here on the right-hand side. And what you'll notice is that these rainbows have little dark lines in them. These dark lines are what we call absorption lines, and they indicate the same thing those emission lines did on the other chart, essentially what the star contains. Notice the star has some sodium in it. See that distinctive double yellow? If I zoom in here on the left-hand side, you'll see all the stars seem to contain two dark lines, or in one case, sometimes a bright line on one of those lines. This is something, and this is something else. Specifically, what you're seeing are the lines of absorption of hydrogen and helium. See this? All stars contain hydrogen and helium because the universe is essentially made of those two elements, overwhelmingly so. So all the stars in this chart will have hydrogen and helium, but they don't all have all these other dark lines. And all those other dark lines indicate different elements, some of which are very rare. Notice this star here, Yale 1755, has lots and lots and lots and lots of dark lines, and that's because this star is very rich in rare, heavy elements. But then compare it to HT 94028, and notice very few lines. That's because this star has very few heavy elements. So we can tell the chemical enrichment, which is, by the way, referred to as metallicity. We can tell the metallicity of all these stars by studying the color of light. In this case, that they absorb, not emit. But it's really the same science in either case. Now, there's something profoundly important about this. We can tell what generation a star is by studying its metallicity. Metallicity is that term we use for the chemical enrichment. Now, the metallicity changes because, like I said, over time, as the universe ages, we get larger and larger quantities of heavy elements. And you can clearly see that by studying the light of young stars versus old stars. This star right here, Yale 1755, is a newborn baby star, whereas HT 94028 is an extremely ancient population 2 star, the previous generation of stars. There are 3 generations of stars, and these two are very different. Yale is a brand new baby star, and HT 94028 is an extremely ancient one. And we can very clearly tell that by looking at their metallicity. And the reason why this is so easy to see is because there's something amazing about the universe. I don't know if you're aware of this or not, but telescopes are time machines. Let me see if I can fit my head on here for a second. Yeah, okay, whatever. That works. The Hubble Space Telescope is hiding under my head over here. So we're looking back in time here. Telescopes are literally, or let's say, kind of like time machines, because light does not move instantaneously, does it? And so when you look at something far away, you are literally looking back in time. And one of the most important discoveries we made was the extraordinary discovery that the farther we look back in time, the less elements there were. We can figure this out by studying the color of light, either light emitted or absorbed. In both cases, the farther you look back in time, literally the less stuff there is. It's not less mass, but it's less, let's say, chemical variety. As the universe gets older, we get larger and larger quantities of heavy elements. This is how we tell the generations of stars apart. We often like to show our visitors here at the observatory objects known as globular clusters. Here's a globular cluster. These are very impressive clusters of extremely ancient stars. These are some of the oldest things you will ever see through a telescope. And if you were to study the spectra of these stars, you would find that they have very few heavy elements. These stars are over twice the age of our Sun, and these, again, are members of population 1. Our Sun is a middle-aged member of the current generation. I wonder if there are any questions about that. Let's see. Dark matter. We don't know. Someone's asking about dark matter. We don't know. We don't know how dark matter is created. We don't know if it exists. If it does exist, it probably is created in the same way other elements are. In the very earliest stages of the universe, there was already hydrogen and helium and a little bit of lithium. If dark matter exists, maybe it was also there at the same time as well. But yeah, I can't answer that because we don't know the answer of how dark matter is created or if it even exists. Questions? Any questions? Let's see. I don't see any questions. Okay. We're going to be wrapping it up in about 6 minutes. I was hoping to give you guys a chance to talk about a few things or ask a few things. I think I'm going to show you something kind of fun. Watch this. I'm going to show you what might look boring. You're going to think this might be boring. You might think it's going to be a school lesson. I'm going to show you a table that you've seen many times in your life, the periodic table of the elements. However, we're using it in a very unusual way. It has been laid out in the way you're used to seeing it. This is essentially how you normally see the periodic table laid out. But notice the name of this table. We've called this here the periodic table of nucleosynthesis. Nucleosynthesis is the origins of elements. The color codes on this table illustrate the origins of the elements. And I don't know if you're aware of this or not, but we now know the origins of all the natural elements. Notice I say natural elements. There are also unnatural elements that humans have created. So let me show you a few things here. The red indicates Big Bang. As you can see, very short list. We got some hydrogen, we got some helium, we got a little bit of lithium, and that's it. But as the universe ages and high mass stars live and die, we get the blue elements on the chart. By the way, the ones with little yellow squares around them, these are elements that make up a significant portion of your body. So the chemicals in your body are literally, in this case, forged by high mass stars via both fusion and fission. Fusion is where you create heavier elements from lighter ones. Fission is where you destroy atoms. And sometimes when you destroy an atom, you'll get new atoms from that process. Notice we see exploding stars. And this includes both type 1 and type 2 supernovas, and also another kind of supernova called a kilonova, caused by the collision of neutron stars. And that's where the green ones come from. Low mass stars are responsible, again, via both fusion and fission for these elements, the yellow ones. See? And then one that I find very entertaining, cosmic ray spallation, is responsible for only 3 elements on this chart: lithium, beryllium, and boron. In fact, this is the only primary source of these 2 elements, beryllium and boron, in the universe. Now, if you're wondering what this is, cosmic rays are very, very powerful events, particles that move through space at enormous velocity and strike other atoms so hard that they can destroy them. And that's that fission I talked about. In the case of cosmic ray fission, sometimes you'll get new elements from that process, including beryllium and boron. Some of you who are keenly observing the image might also notice there's some other colors on here that are not listed. For example, the gray ones. The gray ones are the result of radioactive decay if they have no asterisk next to their name. The ones that do have an asterisk are, of course, made by people. So yes, humans have been busy creating new elements over the last 100 years, and all the ones on this chart with little stars are made by humans, yes. As far as natural radioactive decay, you might notice radon over here. Radon is a very famous element. It's actually bad for your health. That's why a lot of people know about it. It accumulates in people's basements. It tends to happen if your house is built on granite. Granite will contain uranium, and uranium naturally decays into, among other things, radon gas. And so that's an example right there of an element being born not from some cosmic mechanism, but from the natural self-destruction of an unstable element. In this case, uranium. Also thorium. Thorium will also produce radon gas as well. Questions about that? Okay. Hold that thought. Please explain. Okay, I don't see any new questions. Okay. Now I'm just gonna put a random picture on the screen that I think is kind of fun. I want to show you a picture of what we refer to as a cosmic ray air shower. And I'm going to put my face back on the screen here. So what you're seeing here is a simulation depicting an event that occurred over Chicago. That's Chicago there on the ground. You have here an atom in the upper atmosphere, right here, being destroyed by a cosmic ray from deep space. And by the way, cosmic rays are emitted by the most violent phenomena in the universe, like black hole accretion disks and hypernovas and things like that. So cosmic rays are so powerful they can destroy atoms, and you get all these secondary particles. And this is the source of rare elements like beryllium and boron. Yeah. Any questions about that? A lot of people don't know you can actually take pictures of cosmic rays with an ordinary camera. Here's a random picture of some aurora here at the observatory a few years ago. Now I'm gonna zoom in on this picture, and I want you to look for something strange. Look, I'm driving around here looking for something strange. Don't see it. Zoom out over here. Let's go over here a little bit. Let's go over here. Oh, what's that? See that line, guys? This curving line, there's a little one there, and then here, that's a cosmic ray that struck the sensor on my camera. Now, you might think this is some once-in-a-lifetime event. Wow, you caught a cosmic ray on a camera picture. No, this is something you can do almost every night by accident, actually. And I don't deliberately try to get these because they actually can be very distracting during a time-lapse sequence. I know that not only is this a cosmic ray, but that it's an electron because it's making a very small track, and also it's curving. It's curving because the electron is charged. So this is an example of a cosmic ray impact on my sensor. Any questions about that? Now here is a different picture. Here's some cell phone towers in our parking lot. I'm going to zoom in here. I've turned red. Thank you for my wonderful camera here. This cosmic ray here, much bigger, more impressive. This is a cosmic ray alpha particle. This is a helium nucleus that broke off of an atom after being destroyed by a cosmic ray impact. Isn't that neat? Notice it's a very straight line. Does not have a charge. It's not reacting to any charges in the camera. But it is very bright because the helium nucleus of the alpha particle is very, very prominent. Questions about that? It's about time for me to start wrapping it up. It is 7:01 actually. It's 1 minute past. Oh no. Oh no, what will we do? We're over time. I want to thank you all for looking. I don't think we have many people tune in for this, but it's important to still do the show either way because it is being recorded. Those of you who missed it or maybe tuned in late, you have the opportunity to watch the whole thing because the nice thing about YouTube Live is it is recorded in real time, even as we're giving the show. So if you missed something, feel free to back up. Now, with that, I want to repeat what I said earlier at the beginning of the show. We really appreciate Girl Scouts of America. Girl Scouts of the USA is a great organization with very smart, clever, creative young ladies who often ask wonderful questions during our shows, like I mentioned, and often have wonderful answers. So we hope you enjoyed this. We hope it was worthwhile for your time. We appreciate your support, and of course we support you. Those of you who just randomly stumbled upon this, who are perhaps not Girl Scouts, feel free to sign up or subscribe to the Washington State Parks YouTube page. It'll give you an opportunity to see events kind of like this. By the way, it's not just me. We have many state parks in our system, and they also will do videos like this. So with that, I hope you learned a few things. I hope it was worth your time. And I look forward to talking to you again in the future. And by the way, feel free to drop by Goldendale Observatory. We are open. Please check our website, goldendaleobservatory.com. We recently finished a really impressive facility upgrade, and this is a much nicer and much bigger place. So tell your friends, drop on by Goldendale Observatory. But again, please check our website first so you can make sure to come when we're open, and make sure you have a reservation if you need one. So with that, thanks again for your time. Have a good night.